Hello, I'm Petia Kojouharova, and here I am presenting a work by Attila Krejci and me about the different mechanisms driving the change in the size effect in symbolic and non-symbolic numbers. When presented with a task in which you have to choose the larger of the two numbers, two phenomena can be observed, both of which relate to our representation of numbers. One is that people make fewer errors and are faster the larger the distance or numerical difference between the numbers is. This is called the distance effect. The other is that people make more errors and are slower the larger the numbers are, expressed here as the sum of the two numbers. This is termed the size effect. In their seminal paper, Moyer and Landauer stated that the two effects are best explained by the ratio of the numbers, and thus the representation of numbers has psychophysical properties. This psychophysical number representation is called the analog number system, or the ANS, works according to Weber's law, and is proposed to be responsible for both symbolic and non-symbolic number processing, with the distance and size effect stemming from representational overlap. While there is a large amount of evidence that the ANS does process non-symbolic numbers, recent studies have questioned its role in symbolic number processing. An alternative account is the discrete semantic system, or the DSS, which supposes a discrete representation that is similar to semantic networks or to the Mendel lexicon. While according to the ANS, the distance and the size effects are rooted in the numbers ratio, the DSS states that the distance effect depends on the semantic distance between the numbers and the size effect stems from their everyday frequency. So how can we use the size effect to infer the representation of symbolic numbers? If the size effect is rooted in the everyday frequency of the numbers as according to the DSS, manipulating the frequency of the numbers will modify the size effect in symbolic, but not in non-symbolic numbers, because for non-symbolic numbers, the size effect depends on the psychophysical properties of their representation. We investigated that in two separate studies. In a comparison task, we manipulated the frequency of Indo-Arabic digits in one study and the frequency of sets of dots in the other. The distribution of the numbers looked like this in the everyday frequency condition, the uniform frequency condition, and the reversed everyday frequency condition. In the studies, we recorded error rate and reaction time and analyzed them by fitting a size effect regressor to the data and comparing the slopes using the full stimulus space, which I will talk about in a slide or two. In the task, the participants saw a pair of Indo-Arabic numbers in the first study or sets of dots in the second study and had to press a key on the side of the larger number. The full stimulus space is just another, better visualization of distance and the size effects. Instead of pulling together performance by distance or size, each cell represents performance for one number pair. The distance effect is seen as performance becoming better from the main diagonal to these two corners. The size effect can be seen as performance becoming worse along the main diagonal. Darker color here means worse performance. If the size effect depends on the frequency of the numbers, then in the everyday frequency condition, the stimulus space will show both the distance and the size effect. In the uniform frequency condition, only the distance effect will be visible, and in the reversed everyday condition, the size effect will be in the opposite direction. For non-symbolic numbers, we should observe only the everyday frequency pattern, which looks like the one given by the numbers ratio, while for symbolic numbers, it's possible that we'll see all three depending on the frequency manipulation. Note that the full stimulus space will allow us to see any systematic change in its pattern. Here is how our results for symbolic numbers compare to the expectations. For both error rate and reaction time, the usual size effect is visible in all three frequency conditions, but the pattern changes between the conditions. This change is confirmed by the statistical analysis of the slopes of the effect. It changes with the frequency, with the slope being the smallest for the reversed everyday frequency condition and largest in the everyday frequency condition. As for non-symbolic numbers, a change in the pattern is not visible for error rate, but there is a change for reaction time. The statistical analysis of the slopes confirms that the slope doesn't change for error rate, but changes for reaction time, similarly to the change in symbolic numbers. To sum up, the frequency manipulation changes the size effect in Indo-Arabic digits, although it doesn't disappear, but the results for non-symbolic numbers are not what would be expected from a psychophysical representation. This raises new questions. Can we find a better measure of the effect of frequency in non-symbolic numbers? And if an effect of the frequency manipulation is observed in both symbolic and non-symbolic numbers, is it driven by the same mechanisms? To this end, we decided to use a version of the diffusion model analysis, the easy diffusion model. Diffusion model analysis helps to reveal background mechanisms of the decision process, and the easy diffusion model recovers the following parameters: drift rate, threshold, non-decision time. Very simply put, when making a decision, a part of the elapsed time is not related to the decision. Within the time that is related to the decision, information starts accumulating, as shown by the drift rate, until a threshold is reached and a decision is made. The analysis that follows is preliminary. We are still exploring both its feasibility and ways to make it more precise. An important consideration was that the different number of trials in the cells could bias the results of the diffusion model analysis because of the edge correction used in the model. To rectify that, we only chose cells along the main diagonal of the full stimulus space, in other words, cells containing small, middle, or large numbers. We then chose randomly 6 trials for each. This was the smallest possible number of trials in a cell, pulled the trials together, and tested the effect of the frequency. Note that in this analysis, the sensitivity to patterns that we see in the full stimulus space is diminished. The results for the 3 frequency conditions in symbolic numbers confirm the effect of frequency in error rate and reaction time, and also show this effect in the case of drift rate and non-decision time, as seen by the interaction between the 3 conditions. The change was largest from small to large numbers in the everyday frequency condition, and smallest in the reversed everyday frequency condition. There was no effect on the threshold. For non-symbolic numbers, the size effect is very clearly observed for error rate, reaction time, and drift rate, but there is no effect of frequency. The results for the reversed everyday frequency condition seem to differ for threshold and non-decision time, but neither the interaction nor the main effect of frequency are significant. To sum up, in the case of symbolic numbers, the size effect is rooted in the frequency. As for non-symbolic numbers, the manipulation of the frequency affects the size effect, but the mechanisms behind the change are not that clear, even though they seem to differ from those for symbolic numbers. A possible explanation for the diffusion model analysis results is that this analysis does not work reliably for methodological reasons, the different number of trials in a cell, or cells with zero error rate. Some of the partial results point to the threshold as being affected by the frequency manipulation. Thank you for choosing our poster. If you are interested in our work, you can check our website, thenumberworks.org. You can also follow us on Twitter.